All right, so we're on 1B 9 through 10, part A. We're talking about rational functions with vertical asymptotes and wholes. So we're going to keep building on those concepts so that we have it solidified. Does that make sense? So once we get it down, I think you'll be like, oh, that's not terrible. Okay. So up first, in the previous lessons, we've talked about what a rational function is, which is just a ratio between two polynomials, right? I have a polynomial in the numerator and a polynomial in the denominator. That's all that is. That's what makes it rational. The main thing that makes it irrational is the denominator, the fact that you have variables in the denominator, right? Okay. Now we're going to dive a little deeper into the vertical asymptote. We're going to dive just a little bit deeper into what the vertical asymptote is in sense of how do we find it? How do we practice? How am I supposed to make sure I understand this full-heartedly? Okay. And then our whole is when we can remove. That's called our removable discontinuity. Our whole is our removable discontinuity. Okay. Okay. That says removable discontinuity. I think it does. Close enough. All right. Discontinuity. Yep. That's the second word. Okay, fine. I'll fix it. All right. So forget it. You know what it says, guys. You know what it says. Okay. All right. Now, note the degree, which is our multiplicity of the common factors, and their location in the rational function will be important. So making sure that you can tell me the degree of the polynomial is important throughout this whole thing. Got it? And at this point, you should be able to do that because that was a main part of Algebra 2. Okay, so when we're looking up here, we have vertical asymptotes. Algebraically, we are looking at our denominator, right? Algebraically, we need to be in factored form. So first off, everything has to be factored, which we know, right? After we look at the factored form, the second thing we're looking to see is anything can be eliminated, right? If nothing can be eliminated, great. That's how I know what's left in the denominator is a vertical asymptote. Okay, it's a vertical asymptote if it can become zero. Make sense? So if you look at this graph, and I have x minus 2, when I take x minus 2 and I set it equal to 0, that means that x would be 2. And because if I plug 2 in, it's going to make a 0 my denominator. That's where my vertical asymptote lies at. My vertical asymptote is at x equals 2. Remember, it is okay for 0 to be in the numerator, but it is a no-go for 0 to be in the denominator. Okay. Okay. So when you're finding your vertical asymptotes in your own words, this is your space. So this is so that you can show that you understand what we just did. Right. What are you doing? So finding the vertical asymptote in your own words, take a minute, take what we just did, and write what we did. Y'all don't have the space to write? Did I get okay. This was supposed to be added to your notes this year to make you interpret yourself. So take a moment at your table and tell your neighbor how to do it. Go. Dang it. All right, here we go. Thank you for taking the moment to explain to your table how do you find a vertical asymptote. Okay. Now let's talk about the limit notation. You're going to have to write this part in because apparently it is not in your notes. All right, limit notation is simply asking you as you're approaching your asymptote, what is happening? Okay. So if you look right here, it says as your limit as x goes to 2, this negative says you're coming from the left. Does that make sense? So that little negative right there says as you're approaching 2 from the left, what is your function doing? So as I'm coming towards my asymptote from the left, what is my function doing? It's going to negative infinity. Do you see that? Yes? Okay. And then the next one says limit as x goes to 2 from the right. That's what that plus signs mean. As I'm coming from the right, heading towards 2, what am I doing? I'm going to positive infinity. This is your limit notation for a vertical asymptote. Okay, you're going to have to write it in. Okay. All right. Okay, so again, when you're looking at it as you're approaching, so if I gave you a limit and there's a numerical value and I'm saying coming from the left and from the right, that lets you know at that point that there's an asymptote. Does that make sense? Okay, if those two values are going either to positive and or negative infinity, that's an asymptote. If they were approaching a number together, then that would be a whole. That's the difference here. Okay. So we're going to talk about that in a minute. But if I was approaching from there to there, then it would be a whole. I mean, a number, a value, not a whole, a value. Like it was defined. Like let's say as I come from the left of 2, the right of 2, and I say it equals 5. That means that there's a point, right? Because they're both coming at 5. So it'll be 2, comma 5. So I'm approaching 5, right? In this case, there isn't a point. They're just going on forever and ever and ever, right? Forever and ever and ever. Okay. That lets me know that this is a vertical asymptote. So this is a limit of a vertical asymptote. Okay. Now, let's talk about a whole. So going to the other side. Wholes. So with your whole here, that means that there's a removable discontinuity, meaning that there's a factor that I can eliminate from the denominator that will be removed. So it's something that would have made my denominator equal to 0, I am taking it out. Okay. So when you look up here, I have x minus 3 and x minus 3, right? So I'm removing that from the problem. Okay. They're canceling. Well, yes, but we're removing them because it equals 1. Okay. So that therefore we're just left with 2x minus 1 over x minus 2. Okay. But I had a removable discontinuity, and that removable discontinuity is 3. So we have a whole at x equals 3, which is still a discontinuity. There's a hole in my graph right there. Okay. Okay. So a lot of times you're not going to clearly see that hole, but when you go to the table and you go to that value, you'll see that there is a error, right? It'll say undefined or error or something to that degree. Okay. So graphically, when you're looking at it, notice that I have 3 discontinuities here, right? I have a horizontal asymptote at y equals 2, which makes sense because the degree of my numerator and the degree of my denominator are the same. So all I'm doing is using their leading coefficient, correct? Okay. I have a vertical asymptote at x equals 2, which makes sense because what was left in my denominator? The x minus 2, right? And so if I plug 2 in, that would make it 0 in the denominator, and it's a no-go for 0 in the denominator, okay? And then you can clearly see my removable discontinuity at x equals 3. Okay? All right. So we're going to pause for a moment, and at your table, you're going to explain to each other, how do you know if you have a hole in your graph? Okay, so let's dive a little deeper. Now, I heard you guys explain to each other how to find it. So good job for the most part, even though maybe not the words I wanted, but you did. Okay, now the next thing is if the problem asks you for the coordinate of the hole, you're going to plug it into your simplified, what was simplified. So if I'm looking for what the y value is, I have to plug it into the simplified value. Does that make sense? So like to know exactly where this is located. Are y'all with me? All right, so I'm going to work it out. So for example, we know we have a hole at 3, right? If it wasn't a hole, what would it be is what it's asking you. So if it wasn't a whole, what would the y value be is what it's asking. To find what that y value would be, you're plugging it into your simplified rational function. Does that make sense? So I will be taking x equals 3 and plugging it into the simplified version of it. Okay, so I'm going to plug in 3, and we get 2 times 3 minus 1 over 3 minus 2. What is 3 minus 1? 2. What is 3 minus 2? 1. So the whole is actually at 3 comma 4. Does that make sense? Does it, even looking at the graph, can you see that it's at 3 comma 4? You can see that that's where it would be. It would be at 3 comma 4 if it wasn't a whole. Okay? You don't take your whole and plug it back into the original because it's going to make it 0. You take the whole and you plug it back into the simplified. Yes. Okay? All right. Up next is the limit notation of the end behavior. So the last thing here is looking at what's happening as you are going forever to the left and forever to the right. When we are going forever to the left and forever to the right, if it equals a number, so notice how I'm equaling a number here. This is a sign that you have a horizontal asymptote. Okay? So you're adding this. So this is how you know you have a horizontal asymptote. This is how you know you have a vertical asymptote. The difference is what you're approaching and what your outcome is. So for vertical asymptotes, you are approaching the number, right? From the left and from the right, and your outcome is infinite. Do we see that? For horizontal asymptotes, you are approaching infinity from the left and from the right, and your outcome is a number. You see the difference? Okay, vertical, we're approaching the numbers from left and right, and our outcome is infinity, positive or negative infinity. Horizontal, we're approaching infinity from the left or from the right, and our outcome is numerical. We see the difference? So if I gave you a limit and I said, is it a horizontal or a vertical? You should be able to tell me that this is describing a vertical and this is describing a horizontal based on what they're approaching and on their outcomes. Yes? We see it? All right, this is where we're going to stop at today. All right.